Okay, so this is going to be the Quiz 7 walkthrough. And we're going to go through each of these questions and talk about them. Quiz 7 was a less math heavy, but it's more focused on chemical reactions, how to predict those products, and really some of the basic things about chemical reactions as well. So looking at number 1, which of the compounds in the following reaction is a liquid? We have sodium chloride, H2O, water, reacts to form sodium hydroxide and hydrochloric acid. So what I was looking for in this question is that you were looking at these subscripts, or these little, you're looking at these down on the side where we've got this S, L, AQ, AQ. So for this problem, and for any problem, for any reaction, S is solid, L, which if you're writing it by hand is usually a cursive L, is your liquid. And then the NaOH here with the AQ means aqueous. So aqueous means that it is something in water. So water is a part of it, and then there's excess water around. So here I was really looking for that you knew that L was liquid, right? So that's why H2O is our correct answer. So just a little bit of the sort of how we write chemical reactions. So now for number 2, we're going to complete and balance the following reaction. So we have potassium sulfide and we have silver nitrate. So we need to predict what these products are going to be. And then it says, which of the following would be one of the products? Don't forget to consider solubility, which is a big hint that we'll probably have something that is insoluble. So this is number 2. We have potassium sulfide, aqueous, plus silver nitrate, also aqueous. And for most chemical reactions, you can take your cations and you can swap them while leaving your anions in the same order. So what I mean by that is, we can come over to the other side here and we're going to have sulfur combined with something. We don't know if that's going to be solid or liquid yet. And then we're going to have our nitrate, or NO3, and that's going to be, right, solid, liquid, or aqueous. And then on the left here, silver was initially combined with nitrate. So now on the right side, we're going to put silver with the sulfur, and we're going to potassium with nitrate. Now we're not quite done yet. So we've predicted our products, but we need to make sure that our charges are balanced. So silver has a 1+ charge. That's one of the special ones you have to memorize. Sulfur is in 6A, group 6A on the periodic table. So it's a 2- charge. So when we combine silver and sulfur, if we think about our ionic naming rules, then we have silver as a metal, so that's our cation, and we have sulfur, which is our anion, and in ionic compounds, we need to balance the charges. So since sulfur has a 2- charge, and silver has a 1+ charge, we need to have 2 silver atoms to cancel out the charge on the sulfur. So to do that, I'll just add a 2 here. We can actually even erase this. Ag2S. And we need to do the same for our potassium nitrate. So from the periodic table, potassium is in group 1A, so it has a 1+ charge. Again, this is an ionic compound. And then nitrate is one of our polyatomic anions that you need to memorize, and that's a 1- charge. So those are already balanced. We have nitrate with 1-, potassium with a 1+. Those charges cancel out. One last step. We have to balance these. So to balance these, we need to have the same number of atoms of each element on the reactants and the product side. So if we look on the left side, I usually just pick one to start with, and then you kind of work your way around. So let's start with potassium. We have 2 potassiums on this side. We know that because of this subscript. And on the right side, we have 1 potassium. We know that it's 1 potassium because it doesn't have a subscript. So what we do is, once we've balanced our ionic compounds, we can no longer change their subscripts. But we can add coefficients to change the number of each atom or polyatomic ion. So I'll add a 2 here for potassium nitrate. So now we have 2 potassiums and we have 2 nitrates. So once I've done that, I've changed the number of nitrates on the right side, so I need to go back to the left side to see if that matches. So we have, because of this 2 coefficient, we have 2 nitrates, but on the left side, we just have 1 nitrate. So again, we'll do the same thing. We just add a 2. So now we have 2 nitrates, because this is nitrate times this 2 coefficient, and then nitrate times this 2 coefficient. But now we've changed silver. We changed the number of silver atoms. So we have 2 silver atoms here. And we go to the left. And because we have this 2 subscript, because we balance these charges, that's already balanced. We don't need to add another coefficient to get more silver to match the left side because they're already matching. And then we look at our last element, sulfur. Don't get confused by this number 2 that is separate from the equation, but we have 1 sulfur and we have 1 sulfur. And so as a final check, if you want, you can take all of your elements and write them out. So we have potassium, and we have 2 of those, sulfur, we have 1 of those. So I'm just counting all of the elements on the left side here. Silver, there's 2 silvers, and then nitrate, we have 2 nitrates. So we'll keep things in the same order on the right side. I'll do potassium first. And I'm just counting the number of atoms here, so it doesn't matter really which order you go in. For the reactant side, I just went left to right. So potassium, sulfur, silver, nitrate. The right side though, because we want to compare these, I'm going to keep these the same. So we have a 2 coefficient in front of our potassium nitrate. So we have 2 potassium. We have a single sulfur, silvers, silver atoms, right? 2 coefficient here. So we have 2 of those. And then NO3, again, this 2 coefficient means that we multiply this entire molecule by 2. So we have 2 nitrates as well. And then just comparing back and forth, we have 2 and 2, 1 and 1, we have 2 and 2, we have 2, 2. So now we have our completed and balanced chemical reaction. So now though, with our new products, we know that our reactants were aqueous, but now, because the question especially said, don't forget to consider solubility, we'll use our solubility table, which I recommend having on hand for exams. And the way that you read this table, so these compounds up here, compounds containing the following ions are mostly soluble. And then there are some exceptions. And then in the second half, compounds containing the following ions are mostly insoluble, meaning that they form solids, that they don't dissolve in water. So then there are also exceptions for these. So if we look at our equation, let's look at silver sulfide first. So is silver on our solubility table? It is. So we have silver here, but it's not combined with chlorine, bromine, or iodine. So it doesn't help us out there. Is silver anywhere else on the solubility table? And it's not. So now we'll move to sulfur and say, okay, sulfur on the periodic table. So sulfur's here, and that's under compounds containing the following ions are mostly insoluble. So you would say that, okay, anything formed with sulfur is going to be insoluble unless it's paired with these exceptions. So lithium, sodium, potassium, or ammonium would be soluble. Calcium, strontium, and barium would be soluble. We have sulfur, which matches to this. And then silver is not on this list of exceptions. So this compound is solid. It's insoluble. For potassium nitrate, most things forming with potassium are soluble, and most things forming with nitrate are soluble. So both of those form soluble compounds. So this would be aqueous. This is a very, very multi-stepped problem. They kind of have to be written this way so that I can put them on the exam. So we've completed and balanced the following reaction. I'll just write this in here, Ag2S solid plus 2 potassium nitrate, aqueous. Now the question is, which of the following would be one of the products? So, and you need to make sure that matches every part of this. So, right, this is Ag2S, which does match with this one. So silver sulfide solid is the answer here. This is wrong because it doesn't have the correct coefficient. This is wrong because it's aqueous. And this one's wrong because it's aqueous as well. So when I write these problems, there will be a lot of similar answers. And that's because I am testing to see if you know exactly what to look for and not just approximately. Let's move on now to number 3. So classify the reaction you balanced in question 2. So this involves you knowing the different types of reactions that were covered in the lecture. So an acid-base reaction is going to involve acids, so something like hydrochloric acid or sodium hydroxide usually. And really what you're looking for in those acid-base reactions is this hydrogen first, or if you have an acid as a part of the reaction. Oxidation reactions we cover very briefly, and that involves, can't think of one off the top of my head, but a change in the oxidation state of one of the elements. Gas evolution reactions usually involve...
Here's a table of the common gas evolution reactions. Products. Use this or a table from the book.
And a precipitation reaction involves taking two liquids, didn't mean to use the eraser there, involves taking two liquids, like we have here, or two dissolved compounds, and getting a solid. So the correct answer for this problem would be a precipitation reaction. Another good thing to do is to take these things, make yourself a cheat sheet. It's an open note, open book test, but I promise you if you make a cheat sheet, you'll do better because you'll have to take the time to make that cheat sheet, right? So things like acid-base, definition of an acid-base reaction, oxidation reaction, gas evolution reaction, precipitation reaction, that's all good stuff to have on a cheat sheet, quick at hand. And it'll help you memorize it just to make that cheat sheet. So for number 4, we're asked which of the following is the only product in the net ionic equation for an acid-base neutralization reaction. And this is, excuse me, Mochi. This is where it's really important to know your keywords because this might be overwhelming if you don't know what these things are. So a net ionic equation is where we take all of our ions, so we can have things like sodium chloride. When we add sodium chloride to water, these ionic compounds often dissociate, so they fall apart, and the ions spread out. And so you'll get sodium chloride becomes, becomes Na plus Cl minus. And so you get these individual ions floating around in the solution. If you watch the lecture, you should know this. And then in acid-base neutralization reaction, we would have something like sodium hydroxide plus hydrochloric acid, for example, reacts to form sodium chloride plus H2O. So in these reactions, when we do the complete ionic equation, we would write out all of these individual ions, Na plus OH minus plus H plus Cl minus. So just like I broke this here into sodium and chlorine, or sodium and chloride, we have sodium and chloride here, so I just split those out. And then that becomes, we'd still have Na plus Cl minus plus H2O, because H2O is not ionic. So in our net ionic equation, we cancel out all of the elements on the left and right that match, all of the ions. So it's like subtracting both, or in this example, it's like subtracting sodium from both sides. So sodium's, hold on. Notability's freaking out on me. Okay, we back. So sodium cancels, and chlorine cancels. Oh well, things got moved around too. And when that happens, all we're left with is OH minus plus H plus goes to H2O. So the only product that we have in the net ionic equation for an acid-base reaction is water, because the hydrogen ion combines with the hydroxide ion to form water, and all of the other ions cancel out. Nope, nope, nope. What happened here? All right, I'm sorry. Man, Notability is having a heck of a time. Oh, I see what happened there. Okay, well that looks weird, but we're just gonna have to live with it. Okay, I'm just gonna make some room so we can work on. So number 5, consider the imaginary oxide compound XO2, where X is an imaginary metal and O is oxygen. What is the oxidation state of X? So we want to report our number then as an integer. So when we determine the oxidation state, here. Oh, that was cool. Okay, so when we work with, So for number 5, it says, consider the imaginary oxide compound, XO2, where X is an imaginary metal, and O is oxygen. What is the oxidation state of X? And we want to report the number as an integer. So for oxidation states, we want to refer to this table. So this table is hierarchical, which just means that the top one has the highest priority. So it's 1, 2, 3, 4, 5, 6. So if we have an element that's higher on this list than another one, it takes priority in terms of what its oxidation state is. So with something with a metal, we have to determine the oxidation state from one of these groups, whether it's fluorine, hydrogen, oxygen, or group 7A, group 6A, group 5A. In this example we're given, we have X is an imaginary metal, and we're trying to determine the oxidation state of X. And we're given oxygen. So the oxidation state of oxygen, we just grabbed from this table. And something that I always thought was convenient is that it matches its charge that we would get from the periodic table. So oxygen is in group 6A. It has higher priority than the other elements in 6A, but oxygen still has a -2 oxidation state. So if we have a -2 oxidation state, and we have 2 oxygens, so I'm getting this number, 2 oxygens there, the -2 from our table, then the oxidation state on oxygen is going to be -4. And in any ionic compound, so in an ionic compound, the charges must equal 0. So what then does our oxidation state on X have to be? So the oxidation state then, if you're looking over here, our oxidation state on our imaginary metal X is 4. So oxidation states aren't too crazy, but again, add this list to your notes or to your cheat sheet, and you'll be able to find it easily. Okay, so that's number 5. For number 6, this is a very similar problem. But it says, sort the following ionic compounds by the oxidation state on the metal. So again, we're going to be using our list here to determine the oxidation state on our metals. And in general, the oxidation state is the same as the charge. Conceptually, not identical, but very similar. So for this first problem, we already know from the previous problem that oxygen has a -2 oxidation state. And since we have 7 of them, we just multiply that by 7. So our oxidation state is -14. But we have 2 manganese. So to get the charge on a single manganese, so if we have, so we know the charge on both of the manganese together has to be 14. So it has to cancel out the charge on oxygen. So 14 is equal to 2 times the charge on manganese, or the oxidation state on manganese. So we divide both sides by 2. Then our oxidation state is, for a single manganese, is 7. Positive 7. So that's what I'm looking for on these questions is, on a single metal, what is the oxidation state? For this next one, like I mentioned before, the oxidation state is almost always the same as the charge, or what we call the charge. So for this one, we have nitrate, NO3 minus. So the overall oxidation state on nitrate is going to be -1. We multiply by 4. So then we have a -4 oxidation state for nitrate. So that needs to be balanced by the oxidation state on manganese. So in this case, and maybe to help you out, make it a little bit more formulaic, we can say that the charge on manganese needs to be equal to 4 Okay, so we have nitrate now, which has an overall oxidation state of -1. Like I said, it's usually the same as the charge, almost always. So here we have -1 charge, or -1 oxidation state, times 4 nitrates. I'm just getting that from here. So that equals an overall charge of -4. So now the charge on our manganese is just going to have the opposite sign of that. So it's going to be +4. So I guess I should write over here, this is +7, this is +4. All right, charge on a single manganese. For this next one, we're going to have iron, but we need to know the oxidation state on iron. And we determine that from the oxidation state on our anion, just like we determine the charge on the iron when we're naming ionic compounds. So this is a polyatomic anion. You just need to memorize the charge. It's a 3- charge. So we say it's then a -3 oxidation state times just 1 phosphate is an overall charge of -3. So then our oxidation state is just going to be, our oxidation state on iron is going to be the opposite charge, or the opposite sign of our oxidation state on our anion. So it's going to be +3. Sulfate's a similar thing. Again, I'm really hammering home on these polyatomic anions. So sulfate is SO4 2-. Again, it's a charge you have to memorize. So it's a -2 times a single one of those will give us an overall charge of, an overall oxidation state of -2. So then the oxidation state on iron has to be the opposite sign. So it's going to be +2. Sodium sulfide, our last one here, we're going to be, again, like we did before with manganese oxide, relying on our table of oxidation states. So we'll come back up here. So sulfur, or sulfide, is in group 6A. So it's a -2 oxidation state, which is the same as its charge based on its location on the periodic table. So if we say sulfur, the 2-, so it equals a -2 charge, and there's a single one of those, multiplied by 1, equals -2. And now because we have 2 cations, we need to divide our charge by the number of cations. So -2 divided by 2 equals -1. But because our cation needs to have a positive charge, we just flip the sign, so it's a positive 1, so +1 for each sodium metal atom. So this list is already in the correct order, but that's how you do that kind of problem. You're really just determining the charge on the metal. And by determining the charge, that tells you the oxidation state. All right. Number 7. Again, we're sorting the molecular compounds by the oxidation state on the first element. So now this is a little bit different in that we're no longer looking at ionic compounds, but we're looking at molecular compounds. And when we're using molecular compounds, we're going to rely entirely on this list of our oxidation states. So for our first one, we have PF5, so phosphorus pentafluoride. So we'll go over to a list, and we're going to see which of our elements is on this table and how high they are on the table. So fluoride immediately is our number 1, right? So this is our highest priority. So that one is the one we're going to use to determine the oxidation state on phosphorus. So fluorine, that's a -1 oxidation state. And we multiply that by 5. So the overall oxidation state is -5 for all the fluorines. And now we flip the sign, so change it from a negative to a positive. And our oxidation state on phosphorus is going to be +5. So for the next one, we have sulfur dioxide. And we'll look at this list again. So we have fluorine, hydrogen, oxygen. So oxygen here is number 3. This is convenient that sulfur is listed here. So sulfur is in group 6A, but it's lower priority than oxygen. So we'll use oxygen's oxidation state of -2 to determine what sulfur's oxidation state is. So you're looking for the highest element on the list in your molecular compound and using that to determine the oxidation state of anything that's below it. So oxygen is a -2 charge, and we multiply by 2 because we have 2 oxygens. So then the overall oxidation state is a -4 for all of the oxygens. If I ever ask you what the oxidation state is on a single element, I want it on a single atom. So what's the oxidation state on oxygen? In this case, we're looking at sulfur. So we're going to flip the sign on this because we only have one of these. So +4 is the oxidation state on sulfur. For number 3, we have cyanide, but we have carbon and nitrogen. So with carbon and nitrogen in mind, we're going to move over to our table. And we're going to say it's not fluorine, hydrogen, oxygen. Group 7A, oh, that's chlorine, bromine, iodine, those guys. 6A is none of ours. But nitrogen is in 5A, and this table hopefully has nitrogen there. So we're going to use nitrogen's oxidation state of -3 to determine the oxidation state on carbon. And this has a little bit of an additional twist. So nitrogen is -3, and we're going to multiply by 1 because we only have one of those. So it's a -3 charge. But before we can go and say that we flip the sign and make carbon a +4 charge, we have to look at this charge up here. So if we have a charge on our molecule, we're going to add that to the oxidation state. So we have to look at this charge up here. And we're actually going to subtract that from the oxidation state of our other element. So this is going to be -3 minus a -1. So this will end up being, because negatives cancel each other out, we're going to get -3 plus 1. So then we're going to get a -2. And we'll flip that sign to get the charge on our carbon. So this is a +2 charge. Because when we have the charge, we have the oxidation state on carbon is +2, and the oxidation state on nitrogen is a -3. When we add these together, the charge that we get, or the number that we get, needs to be equal to this charge at the top right of our molecule. So that only applies when we have this extra charge on our molecule. Okay, for this last one, actually ends up being the easiest one because we are sorting the following molecular compounds by the oxidation state on the first element. So our first element here is hydrogen. And if we go over to our table, oh, how about that? Hydrogen is number 2 on our list and supersedes oxygen. So then we'll actually use +1. We can just say that our first element here, +1. So of course these are already in the correct order because these are all the answers. Okay, last question here, number 8. Match each reaction type with its defining characteristic. So this is what I was talking about earlier. You can make a list of these for your cheat sheet, which I highly recommend. If it produces a gas, just a gas, then it's a gas evolution reaction. The one that does get confusing is the combustion reaction, which does also produce a gas in CO2. But specifically, combustion reactions involve CO2, water, and heat. For a redox reaction, it primarily involves an exchange of electrons. Again, we only cover these briefly, so I probably won't include many redox. There'll probably be one redox reaction on the exam, but not a lot. It will do oxidation states, but not redox reactions. So primarily involves an exchange of hydrogen ions, and that's our acid-base reaction, like we saw earlier. Because you always have some sort of acid reacting with something else. So if there's an acid involved, it's because that acid is exchanging its hydrogen ion around. There's not much more else to say about number 8. I hope this was helpful. Yeah, good luck on the rest of the stuff.